section 3.10. First, let me go back to section 3.8. Note that in order to find the general solution of a system of n differential equations, we need n linearly independent particular solutions. So once again, suppose we have a system x dot is equal to ax. Let me remind you that if we have a system x dot is equal to ax, where A is an n by n matrix, in order to find its general solution, by theorem 5, we need n particular linearly independent solutions. Now, section 3.8 says that a particular solution of our system can be written as e to lambda t times v. So, if we can find n linearly independent eigenvectors, then we can find n linearly independent particular solutions. However, sometimes we have an n by n matrix, but it is impossible to find n linearly independent eigenvectors. Here's an example. Please take a look at this 3 by 3 matrix. Unfortunately, for this 3 by 3 matrix, it is impossible to find 3 linearly independent eigenvectors. Here's why. Work. It is easy to see that the characteristic polynomial of this matrix is over here. Here's work. So there are only 2 distinct eigenvalues, 1 and 2. And then if we apply the standard procedure, we will see that for lambda is equal to 1, the corresponding eigenspace is only one-dimensional. For lambda is equal to 2, the corresponding eigenspace is again one-dimensional. Since both eigenspaces are one-dimensional, it is impossible to find 3 linearly independent eigenvectors. We can find only 2. Here is particular example of eigenvector number 1 and particular example of eigenvector number 2. Therefore, eigenvectors can give us only 2 linearly independent particular solutions of our system. For example, particular solution number 1 and particular solution number 2. But in order to find the general solution, we need 3. How can we find the third one? If just one particular solution is missing, we apply this formula. If 2 particular solutions are missing, we apply this formula and this formula. In this course, we will discuss cases where either one particular solution cannot be deduced from eigenvectors or 2 particular solutions cannot be deduced from eigenvectors. So, in this course, it is enough to know formula number 1 and formula number 2. Let us talk about these formulas. In these formulas, a lambda is an eigenvalue, but V is not an eigenvector. Remember what is an eigenvector? An eigenvector is a non-zero solution of this equation, which is same as this equation. So, an eigenvector is a non-zero solution of this equation. However, in this formula, V is not a non-zero solution of this equation. It's written here, A minus lambda IV should not be equal to 0. V is a non-zero solution of this equation instead. This is what makes the process so complicated and confusing. Number one, the formula is complicated. Number two, V is no longer an eigenvector. It is a non-zero solution of this equation. Moreover, it should satisfy this property, means it cannot be an eigenvector. Lastly, in this longer formula, if we need two additional particular solutions, V is a non-zero solution of this equation, provided A minus lambda I square V is not equal to 0. Now questions.
So if you have two solutions missing, does that mean you have to use both formulas, or does the second one only use one?
For missing solution number one, you use this formula. For missing solution number two, you use this formula.
Okay. So that formula that you showed, it looked like some sort of Taylor series expansion. So theoretically, if you had more unknowns, would you just continue doing that same thing?
Yes. So basically, since you asked me this question, let me explain you what is behind this formula. It's a beautiful idea. Let us go back to this equation over here. X prime is equal to AX, where A is a number. X is a function on T. Note that the general solution of this equation is e to AT times C. We can come up with this formula using separation of variables method, or use the formula for first order equations. So, if we have this, general solution is this. Here's an idea. Suppose instead of X, we have boldface X, and instead of A, we have capital A. Let us try to find a particular solution of this in almost same form as this, namely e to AT. We just replace lowercase a by uppercase A and lowercase c by boldface V. Now, of course, you may ask me a question, can we do it? Next question is, wait a second, how can we raise e to matrix power? Well, let us go back to Maclaurin series for e to x. E to x is equal to this. Now, we have no idea how to raise e to matrix power. We just don't know this matrix operation. However, if in this formula we replace 1 by identity matrix and x everywhere by AT, the right-hand side makes perfect sense, because we know what is a square, we know what is a cube, we know how to multiply matrix by a variable, we know how to multiply a matrix by 1 over, say, 3 factorial, we know how to add matrices. Problem here, we have an infinite sum, but this is fixable. The point that I'm trying to make is the following. When we see this, each matrix power looks like an absurd. But looking at this, it does not look like an absurd, because each individual expression on the right-hand side makes perfect sense. Of course, how can we deal with these type of things? It's a different question. We discuss it over here. But indeed, these two formulas originate from this one. Did I answer the question?
Yes, thank you.